Great to see you here again. You finished another video and we're starting a new one. In the previous video, we looked into the definition and application of quantifiers. In this new video, I will look deeper into binding variables and logical equivalences with quantifiers. Now, the first thing I want to talk about is related to binding variables. And the moment we use a quantifier on a variable, we call the variable bound. As long as a variable has no quantifier applied to it, we call it a free variable. Remember that when we considered propositional functions, these propositional functions contain variables. And it is very important to bind them to turn them into a proposition. And we can turn them into a proposition by allocating a value to the variable. Now, binding a variable can be done by using a combination of what we call universal quantifier. We also call it for all, and its symbol is in fact an upside down A. And we also have existential quantifiers, which is in fact a mirrored E. And of course, we can give value assignments to the variables. The scope is in fact what we call the part of the expression to which a quantifier is applied. A variable is free if it's outside the scope of all quantifiers in the formula that specify these variables. So it's possible when we don't apply some quantifier on a part of the variables, these may be still free. Let's have a look at some examples of bounding variables. First of all, let's look at this statement. There is a value of x for 3x plus 2y plus z equals 25. We can say here also another statement. For all of x, we have p of x or q of x, and there is an x for which r of x or s of x is true. So these are in fact examples of bounding variables. In the first one, we use there exists an x. So x in this case is a bound variable, while y and z are not. And in the second expression, we have for all x, we have an expression p of x or q of x are true. And then there is an x for which r of x or s of x is true. So these are in fact statements that we can consider, and in both cases we have the variable x which has been bound by the quantifiers. Now we look at logical equivalences involving quantifiers. Remember, in proposition we defined also logical equivalences. And logical equivalences were when in fact one proposition or one combination of propositions, a compound proposition, was giving the same truth table as another one. So when the truth tables of those compound propositions or propositions are equal to each other, we said that we, let's say, consider them to be equivalent. Now we can do the same on predicates and quantifiers. We can define the logical equivalence of two statements, S and T, involving predicates and quantifiers, and it's written as S is equivalent with T, if and only if they have the same truth values, no matter which predicates are submitted into these statements and which domain of discourse is used for the variables. So basically, when we have two expressions, two statements, they are equivalent in all cases when their truth tables are in fact identical. Let's have a look at an example. First of all, we have the following statements, or we have to find if they are equivalent or not. So we have for all x, p of x or q of x is true, and we have for all of x, p of x, or for all of x, q of x. If they both have the same truth statements, truth values, then we can say that they are equivalent. And we're going to do this in two steps. In step one, I want to show that when for all of x of p of x or q of x is true, that for all of x, p of x, or for all of x, q of x is also true. In the step 2, we will show that for all of x, p of x, or for all of x, q of x is true, that for all of x of p of x or q of x is also true. So we're basically proving that the statement from the left to the right is true and from the right to the left. Now let's start with that. Step 1, the left-hand side is true, then the right-hand side is true. Now let us suppose that for all of x of p of x or q of x is true, then we can find a value a in the domain for which this statement is true. So for all of x of pa or qa, this is true because the truth values of p of a and q of a are both true or have opposite truth values for all elements in the domain. So p of a and q of a are true, so this junction is true. When p of a and q of a have opposite signs, true or false, it doesn't matter, p of a or q of a is also true. And when p of a and q of a are false, they in fact lead to a disjunction with a false truth value. So now we can say that for x, for all x, for p of a, and for all x, q of a, they're either both true or they have opposite truth values. And also we have the disjunction here. So when for all of x of pa and for all of x, qa, they are true or they have opposite truth values, the disjunction of those two, of course, will always be true. Now we're looking at the second step. Now we're going from the right-hand side to the left-hand side. Now we say that we have the for all of x of p of x or for all of x, q of x, when it's true, we have a value a in that domain, and we know that the disjunction for all of x, p of a, or for all of x, q of a is true, because p of a and q of a are both true or have opposite truth values for all the elements in the domain. Now this also leads to the conclusion that for all of x, pa, and for all of x, qa are either both true or have opposite truth values. So pa and or q of a is the same. So when p of a and q of a have the same truth values, true values, when they are both true, or they have opposite truth values, then p of a or q of a is also true. This means that we have proven that the two elements, the two expressions that are true. So for example, in step 1, we have proven that when the first expression for all of x of p of x or q of x, when that expression is true, the other expression for all of x p of x or for all of x q of x is also true. In step 2, we have proven the other expression, the other direction. So we have proven that for all of x p of x or for all of x q of x, when that is true, the for all of x and the disjunction of px and qx is also true. Based on this proof, we can conclude that both of these expressions are equivalent, and we can write the equivalence. So this was about the definitions, about the binding variables and logical equivalences. We know what the binding variables are and how we can define logical equivalences. We found some, we have proven some. In the next session, we will discuss about negating quantified expressions. This was another great job of you because you finished another video, and I'm looking forward to seeing you in the next video. Thank you and bye-bye.